We have learnt that in a diode with metallic contacts, there is a p-n junction, separating the p side from the n side, and a depletion region which is devoid of any charge carriers. The holes are the majority charge carriers in the p side, and the electrons are the majority charge carriers in the n side. We have also learnt that when the diode is not connected to the battery, the n side is at a higher potential and the p side is at a lower potential, and the diffusion current and drift current across the p-n junction are opposite in direction and equal to each other at equilibrium. It is important to note that the diffusion current is due to the movement of majority carriers of the p and n regions from one side to the other. Similarly, the drift current is due to the minority charge carriers of the p and n regions from one side to the other side. In this situation, the separation of charges in the depletion region creates a barrier potential that opposes the diffusion current across the p-n junction. We know that the barrier potential prevents any further movement of charges across the junction. Now, let the p-n junction diode be connected to a battery such that the p side is connected to the positive terminal and the n side is connected to the negative terminal of the battery. When connected in this way, the diode is said to be forward biased. When a p-n junction diode is in forward bias, the potential of the p side is raised, and now the p side is at a higher potential and the n side is at a lower potential. Due to the forward bias connection, the barrier potential across the p-n junction decreases and becomes equal to the difference between the barrier potential V0 at equilibrium and the external applied voltage V. Also, when a diode is forward biased, the width of the depletion region around the p-n junction decreases. The lowering of the barrier potential and the decrease in the width of the depletion region leads to an increase in the diffusion of electrons from the n side to the p side. Simultaneously, the diffusion of holes from the p side to the n side across the p-n junction also increases. Since holes and electrons are the minority charge carriers in the n region and p region respectively, this increased diffusion of charge carriers in a forward biased diode is also called minority carrier injection. As a result of the minority carrier injection in a forward biased diode, the diffusion current increases much above its equilibrium value. But the drift current remains almost unaffected since the rate of formation of hole electron pairs is almost constant and is independent of the electric field applied by the battery. Thus, the diffusion current exceeds the drift current, and a net current flows from the p side to the n side in a forward biased diode. The net diode forward current is equal to the sum of the hole diffusion current and the conventional current due to electron diffusion. This current is in the milliampere range. The net current flowing through a forward biased diode can be measured using the circuit shown here. The diode D is forward biased using the battery B. The diode forward current can be measured using the milliammeter MA. The potential difference across the junction is measured using a voltmeter V. The voltage across the junction can be varied using the rheostat RH. The graph showing the variation of current versus potential difference for a forward-biased diode is called its VI characteristics. The origin is the position of equilibrium when no external voltage is applied across a diode and no net current flows through it. The net current in a forward-biased diode remains zero or negligible until the external applied voltage reaches a certain threshold value. Beyond the threshold value, the net current in a forward-biased diode increases rapidly for small increases in the externally applied voltage. If the current increases beyond the rated value, it can get damaged unless it is protected. The current I in the circuit changes non-linearly with the applied potential difference, and hence the diode is said to be non-ohmic in nature. Now let us study about the reverse bias connection of a PN junction diode. For this, connect a PN junction diode to a battery such that the P side is connected to the negative terminal and the N side is connected to the positive terminal of the battery. Here, the P side of the diode is at a lower potential and the N side of the diode is at a higher potential, since the battery raises its potential more than its value for the unbiased state. When a diode is reverse biased, the barrier potential across its PN junction increases and is given by the sum of the barrier potential V0 at equilibrium and the externally applied voltage V. Also, when a diode is reverse biased, the width of the depletion region around the PN junction increases. The increase in barrier potential width of the depletion region leads to a decrease in the diffusion of holes from the P side to the N side and the electrons from the N side to the P side across the junction. Thus, in a reverse biased diode, the diffusion current decreases much below its equilibrium value, while the drift current remains unaffected. The drift current is now greater than the diffusion current. Hence, a net current flows from the N side to the P side in a reverse biased diode. The net current is small, as the drift current itself is small, and hence the net current is even smaller. The net current flowing through a reverse biased diode is of the order of a few microamperes and can be measured using the circuit shown here. In the circuit diagram, the current in the circuit is measured using the microammeter. The potential difference across the junction is measured using a voltmeter V, and the applied potential difference to the diode can be varied using a rheostat RH. The diode is connected to the terminals of the battery such that its P side is now connected to the negative terminal of the battery, and the N side of the diode is connected to the positive terminal of the battery. The graph showing the variation of current versus potential difference for a reverse biased diode is called its VI characteristics for reverse bias. Under reverse bias, the net current, called the reverse saturation current, does not vary much, with increasing applied voltage, and is almost constant for small reverse bias voltages. Until the applied voltage to the diode becomes equal to a certain voltage, VBR, known as breakdown voltage or cut-in voltage. When the applied diode voltage becomes equal to the threshold voltage or the cut-in voltage, the current in this circuit increases suddenly to very large values, causing a lot of heat to be produced in the diode, and hence the diode can get damaged unless we adopt some precautionary measures. Typically, the threshold voltage is nearly 0.2 volt for a germanium diode and 0.7 volt for a silicon diode. The VI characteristics of a diode in forward bias and reverse bias are shown on the same graph for a comparison between them. We observe that a diode allows a large amount of current to flow when forward biased. In reverse bias, diode allows a very small amount of current to flow unless it is operated in the breakdown region. Thus, a diode is a device that allows free flow of electric current, or we say conducts, in only one direction when it is in forward bias. It allows little or no current to flow, or we say does not conduct, in the opposite direction when it is in reverse bias. We can also say that a forward biased diode offers low resistance, while a reverse biased diode offers high resistance to the flow of electric current. A diode is said to offer dynamic resistance that changes with applied voltage. The dynamic resistance R of a diode is given by a small change in applied voltage delta V divided by a corresponding small change in current delta I.
दोस्तों, यदि आज की वीडियो आपको अच्छी लगी हो तो लाइक कीजिए, चैनल को सब्सक्राइब कीजिए और अपने दोस्तों के पास इस वीडियो को शेयर कीजिए। अगर आपका कोई कमेंट हो तो कमेंट बॉक्स में नीचे जरूर लिखें। थैंक यू।